Oh, well, thanks all for joining us across the world for another exciting Philomania 2020 session. This evening or this morning or this afternoon, talks inverted commas and 3 pre-recorded talks. So really exciting to see them. Great diversity of speakers. It's going to be great. He's going to now talk to us about some information geometry of phylogenetic trees. So I'm excited to hear this talk too. Take it away.
Thank you very much. So can you see the PDF?
Yes, we can.
Okay, perfect. Yeah. All right. Yeah, thanks for having me. I'm very excited. And hello from Göttingen, Germany. It's morning here. And my name is Jonas Lueck. And I'm halfway through my PhD under the supervision of Stefan Huckemann. And today I'm going to introduce a new geometry for phylogenetic trees. So basically a new tree space. And this is joint work with Mariam Garba, Tom Nye, who's also in the audience today, I think Mariam as well, and Stefan Huckemann. And this is, I'm basically presenting a paper that has recently been accepted in the Journal of Mathematical Biology. So let's dive right in. So when constructing tree spaces, one has to kind of also give reasons why one would do that. And estimation of phylogenetic trees usually results in samples of trees. So of course you need to do statistical inference on these samples. That means, for example, you want to compute an average of trees, or if you have 2 different samples, you want to test whether they have the same mean, or maybe also do some kind of dimension reduction, for example, PCA. And of course, statistical analysis is based on the geometry of the sample spaces, where the geometry should be biologically reasonable. And of course, it would be nice if it's computationally feasible so that we can actually use it. To this end, we consider our set of taxa to be fixed, the symbols 1 to n, and n is greater or equal than 3. Let's talk about existing tree spaces first. So I want to introduce very quickly the BHV space. Was first introduced by Billera, Holmes, and Workman in 2001. And the underlying set is basically the rooted phylogenetic metric trees with leaves 1 to n and root, say, 0. And metric just means that each edge has a positive length assigned to it. And how the space is constructed is in the following way. We identify the interior edges of each tree via their split representation. And then the geometry is induced by embedding all these splits into a huge high-dimensional Euclidean space where the dimension increases exponentially with the number of taxa we consider. And what comes out of this embedding is a locally flat Riemann stratified ket0 space, where locally flat just means it's locally a Euclidean space, and also has the geometry locally of a Euclidean space. Riemann stratified, you can think of a union of manifolds, where each manifold carries a Riemannian metric, and the Riemannian metrics are kind of compatible along the boundaries of the different manifolds. And ket0 space just means it's globally of non-positive curvature, which is a very nice property and has some strong implications. For example, that between each 2 points in the space, so in this case, between each 2 trees in the space, you have a unique geodesic connecting them. And that's very useful when you want to do statistical analysis, as you can take, for example, midpoints between 2 points. And as an example, I've depicted the BHV space for 3 taxa. This results in an embedding into the R3. And the 3 rays that you can see here, this is basically the BHV space. And they're glued together at the point 0, which is corresponding to the star tree, which has no interior edge. All right. You can add pendant edges to the BHV space very easily, but by multiplying with an n-dimensionally positive orthant. So basically, you just add n positive edge lengths corresponding to the pendant edges. And now I want to consider a very, very particular event in the BHV space. So consider you have these two trees, T1 and T2, in red and blue. And all these edges have the same edge length L. And what's the meaning when you take the limit where you go with the edge length to infinity? So basically, how you could interpret this is that all the taxa are not related to each other when going with the edge lengths to infinity. So basically, what this means in the limit is that T1 and T2 provide the same information, namely that the taxa are not related to each other. So you could think of the limit as, for example, this forest F here that I've depicted in the middle. And for a metric property, you would want that the distance between those two trees goes to 0 as the edge lengths go to infinity, because they convey the same information. But the BHV space has the property that the distance between those two trees grows linearly to infinity as the edge lengths go to infinity. So it does not have this property. And the same behavior holds true for the tropical palm tree space, which Rudy already talked about in the very first talk of the conference. Just a quick side note, basically. Okay, so it may be a good idea. So we want to define a space which has this property that the metric goes to 0 for edge lengths going to infinity. So it may be a good idea to include forests to the space. And this has already been done, namely by Vincent Moulton and Mike Steele in 2004 in their phylogenetic oranges paper. And they called it the edge product space. And the set of this space is all forests with labels 1 to n, where F is just the forest structure with edges E and also labels 1 to n on the vertices. And note that we can have more than one label on one vertex. So we could have, for example, 2 labels on one vertex. The second requirement for this forest with labels 1 to n is that each unlabeled vertex has degree greater than 2. And thirdly, we have, again, positive edge lengths on the edges. And as an example, you can see for the forest topologies for 4 taxa, for labels in this sense, so that you get a feeling for how these forests might look like. So they may still be a fully resolved tree, for example, or something very strange like this, these isolated vertices that are labeled, and this is labeled twice, for example. And just for the notation, with Dij, we denote the usual distance between labels in one particular forest, where the distance now can be infinity if these labels are in different components of the forest. And if the labels are on the same vertex, we define the distance to be 0. If the labels are in the same component but on different vertices, we just add up all the edge lengths of the particular edges on the unique path between the labels I and j. So Dij is for some fixed forest. All right. Then the edge product space is defined as follows. We take all these forests that I have just defined for a fixed n. And first of all, we reparameterize the forests by taking edge weights instead of edge lengths. So we just take the exponential of minus the edge length, and then we will end up with a number between 0 and 1. And we will define a map, namely we will map these forests with the new parameterization to matrices by just taking element-wise the exponential of minus the distance matrix. And note that Dij can be infinity here, so that's just defined as the number 0. And hence the name edge product space, because the Dijs are usually the sum of the distances, the sum of the edge lengths. And when you take the exponential, you get a product of the edge weights. And then we just define the edge product space as the collection of all these matrices for each forest. And this is then a subset of the n times n real matrices, which induces a topology on the set. And there's a nice theorem based on Buneman in 1971, where you basically have a unique one-to-one correspondence between forests and their respective matrices. So we don't lose any information by just taking the set of matrices. There are some nice properties. The edge product space is a CW complex, so a cell complex. And you can just imagine this as a union, so a topological space where it's a union of different closed sets, where the interior of each closed set is homeomorphic to some n-dimensional or some dimensional cube where the dimensions can differ. And just a quick side note, the BHV space is not a cell complex. And the Wald space, which we will define later, is also not a cell complex. And note that set-wise, the BHV space is a subset of the edge product space, where you take the BHV space with taxa n-1, but you still have the root, so you take this as the nth label, and then you can see that you're basically in a subset of the edge product space. But the drawback is the edge product space is only a topological space, and we have no geometry yet. But we have added the forests. So we want to construct a geometry, and that we will do by construction, by going over the tree index Markov processes. Right. So Markov models on trees are, I guess, well known to this audience. Let's take some Markov process for now on a tree. For example, you could think of the substitution models for DNA, or the simpler model, the two-state symmetric model, where you have a state space 0 and 1. And for this particular two-state symmetric model, the covariance between two random variables at the leaves, I and j, is just 1/4 times the exponential of minus their respective distance to each other. So if you would let go to labels, so the distance between two labels go to infinity, you would kind of see that the respective random variables are uncorrelated to each other. And what you can then do with respect to such a Markov process is that you take the marginal at the leaves. So you just take so you get a joint distribution of the random variables at the leaves. All right. You can generalize this to forests by just defining a Markov process on a forest by saying that two random variables on different components in the same forest are independent of each other. And you can take again in the same way the marginal distribution at the labels. And there's the theorem based on Allman et al. 2008, where you actually find that this is identifiable. So you have a one-to-one correspondence between forests and the respective probability mass functions that we've constructed in this way, where we took the marginal at the labels. And Vincent Moulton and Mike Steele already hinted at that by saying that the edge product space is directly to Markov models via this particular one-to-one correspondence, where we have if the respective matrices of the forest are equal, that's the case if and only if their respective probability mass functions are equal. All right, so we have characterized our forests in two ways. One with matrices, and the other way is with probability mass functions. Now, we want to involve geometry. And for that, we will do, again, a reparametrization. And I always call it the Nye parametrization, because Tom Nye came up with it. And it's just taking 1 minus the edge weights that we had in the edge product space. So then we will end up with a number again in between 0 and 1, but we have the maybe more intuitive correspondence that when the weight is 0, then that corresponds to that the edge length is 0. When the weight goes to 1, that corresponds to when the edge length goes to infinity. So we have orientation preservance. And now our scheme is, so we choose a Markov model with a state space omega. Then for each forest, F lambda can identify it uniquely with a probability mass function. And the next step is to impose the so-called Fisher information geometry. If I want to impose the Fisher information geometry, I have as well to explain what it actually is. And the first 3 bullet points are the definition of the Fisher information geometry, roughly. And what you need is a family of probability mass functions where the parameter space is a manifold. So that's our red condition. And also what you need is that the probability mass functions are strictly positive everywhere. And then you can imagine, well, the Fisher information metric is then a Riemannian metric on this family of probability mass functions. And you can imagine just for small distances, the induced metric from the Fisher information metric is approximately the Kullback-Leibler divergence. And there you can also see why we need that the probability mass functions need to be strictly positive, because we will take a logarithm of them. Now, we need to make sure that both conditions are satisfied so that we can actually use the Fisher information geometry. And we kind of do it in the following way, that we, for now, just fix for one fully resolved tree our set of forests. So now we just only have fully resolved trees, but we can vary the edge weights. And then the parameter space is this theta t. And we know that the fully resolved trees have exactly 2n minus 3 edges. So it's just a 2n minus 3 dimensional open set in R to the 2n minus 3. So it's a manifold. And we define the set WNT to be all the trees. So with a fixed fully resolved tree topology, but with all possible edge weights lambda. Okay, so then we have restricted our parameter space, and that's then a manifold. And for the second condition, that our probability mass functions need to be strictly positive, we have found a nice correspondence. Namely, for some forests with the labels 1 to n, the probability mass function is strictly positive if and only if each vertex of f is labeled as at most once. So as a consequence, we throw out all the forests that have vertices that are labeled more than once. So we just denote the set Wn to be consisting of all these forests that have at most one label per vertex in f. And in particular, for a fully resolved tree, we find that the probability mass functions are strictly positive. And also we find that the set Wn is a subset of the edge product space. All right. Now, how do we actually define a geometry on the whole space Wn? Okay, recall. For each fully resolved tree, we have this family of probability mass functions, basically denoted by WNT, and we can impose the Fisher information geometry on each such subset of Wn. And what we then do is we extend the geometry for each fully resolved tree, T, to the respective boundary of the sets WNT by going to the closed cube 0, 1. But we have to still make sure that our probability mass functions are strictly greater than 0 so that we can actually still extend this geometry and it's well defined. So as a small example, consider 3 taxa. What you then have is the only fully resolved tree that you can have is the one in the gray square in the middle with 3 edges. And now, for illustrational purposes, I fixed lambda 3 to be just 0.5. So we basically have 2 dimensions left, lambda 1 and lambda 2. And you can see this, so I've depicted the square here, where the x's are the coordinates, the lambda 1 and lambda 2. And if you, for example, let both lambda 1 and lambda 2 go to 1, which corresponds to that we let the original edge lengths go to infinity, we will end up with a probability mass function that coincides with the probability mass function of this forest topology here. And in the same way, if we go to the red boundary, so we let just one of those 2 values of lambda go to 1, so the original edge lengths go to infinity, we will basically cut this the respective edge, and we will end up with those forest topologies. So we kind of see that this boundary here is still makes sense, and we end up with elements in our original set Wn. And note that the same holds true for if we let one of those lambda1 or lambda2 go to 0. This edge is just getting smaller and smaller and vanishes at some point, and we'll end up with this or this forest topology. And where we have to be careful is, for example, here, if we let both lambda1 and lambda2 go to 0, we'll end up with a forest topology where this one vertex is labeled twice. So that's corresponding to a probability mass function that's not strictly positive everywhere, and we basically won't use this. So this is not part of our space. But that's also not a problem, because due to the behavior of the Fisher information geometry, this point will be infinitely far away, whereas all the others are finitely far away. Okay, so we have extended the geometry for each fully resolved tree, and then we will glue all these WNTs along their boundaries with the identification via their probability mass function in the limits. And we will magically end up with a metric space Wn, which still depends on the underlying Markov model. And as an example, we'll have a look at the two-state symmetric model, and we consider 5 taxa. And the most important point here in this graph is the red dot. This corresponds to this tree here, T lambda. And we don't really care about these pendant edges. So this tree has 7 edges in total, and we don't care about the pendant edges right now. So just ignore them. We only care about these 2 interior edges here. And the values for the interior edges are basically here plotted in this square. And what we did is we considered geodesics emanating from this red dot with particular initial velocities, namely 0 in the direction of the pendant edges, and then different V6 and V7, so in the directions of the interior edges. And you could basically imagine, although this is a okay, let's first of all explain what this plot actually means. So we have this red dot, and we have geodesics emanating from this red dot into the square. And then we have these contours here, which means that each point on the same circle is equally far away from the red dot. And in this way, we end up with this cobweb. Interestingly, if we go in that direction here to the top right corner, we'll end up in the point 1, 1, which corresponds to this forest that I have depicted here on the right side of the slide. And if we go to the bottom left corner, we'll end up with this tree, which is the star tree on the bottom left. And although this might look like this is infinitely far away, it is not. So both blue points are finitely far away from the red point, and we have an actual distance between them. And also you see that the geodesics are not like just going as straight lines, but they're behaving in different ways. And that means that we also have definitely curvature in this space, unlike in the BHV space. All right. So now we come to the Wald space. So everything I've done before was not the Wald space. What we do now is the Wald space, and that's the new space of phylogenetic trees that I wanted to introduce in the first place. The problem is with all these Markov models that calculations for calculating the Fisher information metric, it requires sums over a number of elements that's exponentially growing in the number of taxa. So that's kind of violating the computational feasibility in a sense. And we want to generalize then the Gaussian process as a solution. We want to generalize the Markov process to a Gaussian process as a solution to that. So our state space will become the real numbers. And very interestingly, the probability mass functions, so the joint density at the marginals, become zero mean multivariate Gaussians with exactly the covariance matrices that we use to characterize our forests in the edge product space with. And we have shown in our paper that these covariance matrices are strictly positive definite symmetric real matrices, n times n, if and only if we are with our forest in our space Wn. Now, the Fisher information geometry on the whole set of zero mean Gaussians with parameter where the parameter is the covariance matrix is very well known as the affine invariant geometry or scaled Frobenius or Killing-metric. And what we then do is the Wald space is then just defined as a subset of these strictly positive definite matrices, and we basically use the induced geometry by embedding these elements in Wn into the strictly positive definite matrices. So what comes out of this is a connected Riemann stratified and geodesic space, where connected means I can connect each 2 points in the space by a continuous path. Riemann stratified is, as I already explained, for the BHV space. So it's a union of manifolds that can have different dimensions and will have different dimensions, where each manifold carries a Riemannian metric and they are compatible along their common boundaries. Geodesic space means between each 2 points we have at least one connecting geodesic. Does not necessarily mean it's unique. And if we revisit our example from the beginning, Wald space satisfies the properties that we wanted to have in the beginning. So the distances actually go to 0. And note that our element f, our forest f, is actually contained in our space. So we can reach the limit in a finite time. That's conclusion 1. Conclusion 2 is Wald space is promising to be computationally tractable. And as an example, we consider 2 trees. And this is the usual picture you would see when you would consider an example in the BHV space. So you have these positive orthons. And we have now here the parametrization via the original edge lengths again. And we have basically transformed our geodesic in the Wald space to the BHV space. And we'll see that while the BHV geodesic goes through the star tree, the Wald space geodesic does not. So that might have some interesting implications about, for example, stickiness at the star tree. It might behave very differently. And one last word to why we actually call it the Wald space. Well, Wald is the German word for forest. So that makes sense, I guess. And the original idea came up, I think, in 2017 by Stefan Huckmann and Tom Nye. And it was in the Black Forest, the Schwarzwald in Germany. So that's a small hint at that. And that's all I wanted to say for the Wald space. So thank you very much. And if you have any questions, just ask them now if time permits, and or write me an email, write me a message, and you can see more in our paper that's on the archive. Thank you very much.
That was a great talk. Is there any questions at all from the audience or online? Any online? No chats. We've got a minute for questions now. Yes.
So on that previous slide, that's fantastic. So the conclusion number 2. So is that a general property where you don't go through, the geodesic doesn't go through the star tree? Is there some general statement here that never happens, or can in your space can it sometimes, does it sometimes go through the star tree? Or?
I'm not sure actually. There need to be more simulations or calculations done, but the way I kind of think of this is you have curvature in that space, and if you think of, for example, a tent where basically the top of the tent might be, in this case, the star tree. And if you have 2 points on the surface of the tent, you would never go over the top. So it might behave like this, but I'm not sure. But this is like my picture I have in mind. But I actually don't really know. That's always the case.
Well, if it's true, it'd be cool to prove that.
Indeed, indeed.
Oh, well, I just want to thank Jonas again for a fantastic talk. If there's any other questions, we can save that for the discussion. Fantastic. Okay, so the last live talk for the night before we discuss some of the pre-recorded ones is from Ana Silva from the Department of Life Sciences from the Natural History Museum. I'm looking forward to hearing about the weather in the UK at the moment. Over to you, Anna.
Sorry, can you hear me now?
Yes.
Yes. Sorry, I forgot to unmute. Good morning from a slightly overcast London. And I have to say that I'm a trained biologist, so there's going to be very little maths in this presentation. And I'm coming from what you might call the side of how phylogenetics are used in the wild and how to find some solutions for people that don't have enough mathematical training or to understand a lot of the papers and a lot of the concepts that you have been explaining here today. So for many of you, the concept of, why is this not working? The concept of islands will be nothing new. So this is just a way of clustering islands by similarity based on branch rearrangement operations. And it's been known for quite a while that the presence of tree islands with very, very disparate sizes can mislead the majority rule consensus into showing the consensus of only the largest island and losing the information from all other islands. And this led to, in the early 2000s, the recommendation that parsimony trees be represented only with the strict consensus. Now, we'll see in a little bit with the example I'll be using why this isn't always an option. So I got interested into this island size problem, partly to see whether there is a way of minimizing the effects of island size in majority rule consensus, and also to see whether these effects are restricted to parsimony or whether the pitfalls that are found in parsimony might also be found in model-based analysis, and we are just not aware of it. So I'll be using this example throughout the rest of the presentation. So this was a study published a few years ago on fossil amphibians, where they were trying to place this novel fossil into the amphibian phylogeny, and this resulted in an extended list amphibia, which has not been traditionally accepted. Now, in their paper, they reported this majority rule consensus, which is problematic because their strict consensus is nearly completely uninformative. So this suggests that there are islands present in the data, and this is possibly a case of large island bias happening. So to find this out, we reran the analysis. We found 882 most parsimonious trees, 5 islands of most parsimonious trees, with the largest one having 486 trees. So over half of all trees are in one island, which means that this is a very, very strong case for presence of large island bias. So perhaps the most obvious way of trying to minimize this bias is to do a partition by island consensus. So we used a majority rule, and we found that each island has corresponds roughly to one distinct topology. And while we have used majority rule consensus, it was fairly popular in the mid-90s to early 2000s for botanists to use the partitioned by island strict consensus to explore the incongruence between the tree topologies they were getting. So we can see that indeed most islands, most trees support an extended, at least amphibious, so an extended amphibian group, but most islands actually support the traditionally restricted group. Now, this brings us to a problem. So do we say that trees are equiprobable, or might it be that because there is one main topological variant per island, we could say that islands are equiprobable, not trees? Before showing you how we do the consensus under the island equiprobability assumption, I just want to convince you that this is indeed a problem of large island bias, because there's the symmetric difference between the majority rule consensus of all most parsimonious trees and of the largest island is of 2. So these are, for all intents and purposes, the same consensus. So when we assume that islands are equiprobable, we can compute a consensus by making sure that each island has a weight of 1. So each island contributes equally to the consensus. If you're doing parsimony analysis, the easiest way of doing this is just to change the tree weights to 1 over the size of whichever island that tree is in. And perhaps, and surprisingly, we find a consensus tree that is far less resolved than the majority rule consensus we have, but does contain more information than the strict consensus. So the symmetric difference between these two trees is 10. So this tree contains more information. Now, the point of doing this weighted by island size consensus is not to hide variations in tree topology, but rather to find those relationships that are supported across all islands. So we can see that these relationships are present in all islands, and then if we want to look at them in further detail, we can then go back to the partition consensus. So this is parsimony. Now, what happens in, let's say, Bayesian inference? So if we analyze the data matrix in Mr. Bayes, we ended up with 1,502 unique and equiprobable trees. So this means that in this case, we can treat the Bayesian tree distribution as in the same way that we treat distribution of most parsimonious trees. Because the trees are equiprobable, we can assume there's only one of each. If there weren't, we would have to worry not only about island size, which is the number of unique topologies in one island, as well as island cardinality, which will be the total number of non-unique trees in an island. So I managed to write a few R functions that allowed me to extract the NNI islands from this distribution. And we ended up with most of the islands had a size of 1, and the largest ones had only 3 trees in them, which means that in this case, there is no large island bias for this tree distribution when working with NNI islands. We don't know about SPR and TPR islands because I started trying to compute the pairwise distances between all pairs of trees, and some of them were taking up to 6 days, so we gave up on that. However, this is a very large tree distribution, which means that this is not a good way of trying to explore whether there is large island bias in Bayesian and in resampling analysis. So we are currently trying to find whether there is the potential for large island bias in smaller tree distributions, and also when we have to deal with non-equiprobable trees. Now, this also led us to a thought, which is that the traditional, so Madison's definition of islands assumes that all trees in an island have an adjacency of 1. So for any pair of trees, you can get from one tree to the other by going through a series of trees that is 1 branch rearrangement away from each other. And you can look at, explore how your incongruence in topology between islands by changing the type of branch rearrangement. So you can go from NNI to SPR, and SPR will identify larger incongruences than NNI does. However, what happens if we relax the adjacency threshold? So what if we think about 2 NNI or 3 NNI islands, or the way to X NNI islands? What this means is that this will allow us to group trees that are not that different from each other, but that will still end up in different 1 NNI islands, simply because the intermediate trees are not present. So in this example, you can see that these trees are in singleton 1 NNI islands, but as we increase the threshold, we can get smaller and smaller numbers of trees. And also, if we were to get rid of this tree in the middle, we would still be able to put tree 1 and 3 in the same island if we increase the threshold to 4. Now, I'm currently exploring the tree distributions, both the parsimony and Bayesian tree distributions we have from the Pardo data matrix with a trying to extract 2 NNI islands, but I've only been able to come up with an exact algorithm to do that, and it's being very, 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 very slow. So what we can say at this point is that we can mitigate large island bias in the majority rule consensus if we either work with partition by island consensuses, or we make sure that islands are contributing equally to the consensus, either by weighting by island size or by doing something like rarefaction or oversampling, where we make sure that all islands will be represented by the same number of trees in the consensus. The jury is still out on whether large island bias is present in Bayesian and resampling analysis. And we are in the process of trying to see how useful extending the island definition to allow for XNNI or XSPR or XDBR islands, how useful that will be to explore minor changes in topological incongruences. With this, I just need to thank my supervisor and co-author Mark Wilkinson, also Natalie and Peter for their patience when I'm trying to get algorithms to work, the herpetology group for putting up with somewhat esoterical discussions about tree topologies that somehow don't include any cute amphibians on them, and also my funding body, and lastly, all of you for your attention. So if anyone has any questions.
Thanks very much for that talk, Anna. We've got time for one quick question again. Anyone got a question? Oh, dude, I was just wondering, with your amphibian trees, what was the data underlying those? Like, was it full genome length reads, or was it just particular genes? Or was it a mix of morphology and...
Oh, so in this case, it was a morphological matrix. So it's only morphological data. And this particular matrix is also not very robust because if I go back to the tree, there is a triad of species that if you break it, so if you take any one of those three out, you go back to only getting island 1. So if you remove any one of Rhylomilaris, Chinostogophus, or Eosicilia from the matrix, you don't have a problem of having multiple islands. You just go back to having either island 1 or island 3 as a result. So there's something very funny going on with that matrix.
Oh, cool. Thanks for filling me in. Okay, we'll leave any other questions for the discussion afterwards. I'd just like to thank our speakers, 3 speakers again. That was fantastic. Now we have our 3 pre-recorded people, which are going to give a quick spiel, like a 2-minute spiel about their talk, just to remind us what they did, and then we'll have a little bit of time afterwards to pummel them with questions after that. So I think we'll start with Marika. She can tell us about her talk on refinement stable consensus methods.
Hi, everybody. It's good to see you. I'm much more awake than last night. So some of your talks, some of the talks went on until 1 or 2 a.m. for me. So I'm really tired. But anyway, I hope most of you have already watched my video. My talk was about it's actually joint work with Michael Hendrickson, and my talk was about a concept that we coined the refinement stability of consensus methods. And what that basically means is if you gain more or new insight into how your trees, your input trees that you got from some method or so, and of which you want the consensus. And if you now, if before there were multifocations, and now you better know how to refine them, then this should, in an ideal world, either leave your consensus tree alone or lead to a refined version of your previous consensus tree. But it should not, whatever you do now, if you just refine the input trees, it should not give you a completely different consensus tree. If a consensus method has this property, we call it refinement stable. And of the established methods, consensus methods that we analyzed, we found that only majority rule and consensus have this property. So we thought that this might be something special, that this might sort of set them apart from all other consensus methods, but quite to our surprise, and this is maybe the main result of our paper, we found that there are actually infinitely many consensus methods that have this property, just none of the established ones other than majority rule and strict. So we could basically come up with a sort of artificial method to generate a new consensus method for any natural number, and that has this property, and that basically shows that there must be infinitely many such methods. But it would now, of course, be interesting for future research to look for more maybe new consensus methods that are also biologically plausible and do have this property. Yeah, that's basically the gist of the story.
Thanks, Marika. That's great. I really enjoyed your talk, by the way. It was fantastic. Nice to get a good overview of the cartoon. Pardon?
Not the cartoon as well.
Yeah, the cartoon was great, wasn't it? Fantastic. Any
I'm sorry
questions?
that there was only one cartoon this time. Everybody knows that I love having more cartoons in my talks, but I don't know, Roger Hargreaves or his children, actually, who inherited the copyright, they sold the copyright to Disney, and I was I don't want them to sue me, so I'm not going to use any Disney cartoons in an online talk. So sorry for that. This time, no.
Oh yes, Mike.
So I have a question, Marika. It's Mike here. Hello.
Hi.
So you said that there are infinitely many consensus methods that are both regular and refinement stable. Right. So what are they? Is it too long to explain them?
No, no, it's infinitely many.
No, all of them. Just one of them would do.
No, it's actually just one construction that we came up with. So what you do is you pick two trees, you construct them in a smart way, and you say, okay, if I have n leaves, so you name n, and I tell you how to construct two particular trees, and I just name their consensus. I say, okay, if T1 and T2 look like this, then the consensus should be something that I choose, which is not, majority rule or strict. And everything else, if your input profile is anything else, then I say, okay, I stick to majority rule. So this means that, and then for this method, which of course has no biological plausibility, because why would you treat these particular two trees any different from all the other trees? But it's quite easy to show if your construction is smart, that you can have regularity and refinement stability for this new method. And that means that for any natural number, because that just gives you the leaves, my construction or our construction shows that there is such a consensus method. Because for the rest of the profiles, you don't have to show anything, because for majority rule, you already have it. And you just have to look at your chosen example and choose this carefully. And then, of course, you can combine them. You can say, okay, if the input profile looks like this, like Marika's construction for 10 leaves, or like the construction for 20 leaves, or like that for 23 leaves or so, then I do her method, her trick, I take her consensus, but for everything else, majority rule. So you can even combine these examples to give you more than, than just counting up the natural numbers. So that's the main idea. But of course, the construction had to be carefully chosen and carefully analyzed.
Thank you.
Any further questions? Any online?
Can I ask one?
Yes.
Of course, please.
Yeah, Marika, yeah, thanks. So I haven't got to see your talk, sorry, yet, but so you may have answered this already in the talk, but did you look at Adam's consensus method or the AHO one? You did, yep.
Yes. So
and
I think there's a brilliant paper by David Bryant from 2003 who has like classification of consensus methods. And I think, if I remember correctly, he names 13 different consensus methods. So far, we have looked at 7 of them, but with AHOs and Adams are 2 of them, and they are both not refinement stable. And yes, this is in my talk.
Caught out.
Could I ask a question?
Please.
So I think from your talk, you define a consensus tree as a single tree that summarizes a forest. And I guess Anna's talk has given one example where a single tree may not capture all the nuances. To what extent does what you said generalize to multiple consensus trees? And is there a reason that we should always be looking for one tree rather than many?
No. So what I've done is basically I just tried to distinguish what are the differences between consensus trees and super trees. So I also looked at some super tree methods. And it's also, if you look already at the 2003 paper by David Bryan, for instance, he also discusses MRP, maximum matrix representation with parsimony, which is a standard super tree method. And he uses it as a consensus method. But in order to do that, he basically introduces a second step where he summarizes the set of super trees into one consensus tree. So it is my understanding that, I mean, some authors, of course, use it differently, but it is my understanding that generally the definition, the very definition of a consensus method is that the output is unique, whereas if the output need not be unique, you have a super tree method. But that's just trying to capture the difference here. And there are other differences, of course. Super tree methods, then the input trees don't have to have the exact same leaf sets and stuff like this. Whereas for consensus trees, you have the exact same leaf set for all input trees. But of course, I mean, biologically, there might be reasons for you to want more than one tree. Of course, I mean, there might be 2 or 3 or 5 equally likely trees that explain your data equally well. So there's no real, I can't say there's a reason. I mean, definitions are patient, so you can define whatever you want, and this is just the way consensus methods are defined. But what I have an example in my talk where when you start with 2 trees and you run MRP or MRC, some super tree methods, you end up with the exact same trees. So this doesn't help you at all. So in this case, a consensus would at least do some consensus. It would summarize the data somehow. So if you have 2,000 trees in your sample and it can narrow it down to 200, maybe that helps you, but maybe not. Maybe the gist of the story is that you want to look at one tree. So it really depends what you want. I can think of scenarios where you would want the one or the other. I wouldn't say one is more, like one is better also. It's just different methods.
Excellent. Is there any other questions from Reka? Okay, well, if there's any others, we can come back after. So next up, we will talk with, I think, Martin. I think you're up next, Martin. Again, a fantastic talk. I really enjoyed it as well. So give us the spiel, a 3-minute spiel.
Thank you. Yeah, so my talk is considering how we calculate or quantify the similarity or difference between pairs or between multiple phylogenetic trees. There are various issues that affect widely used methods such as famously the Robinson folds. And one solution to get around that is to compare a tree split by split, find the splits in one tree that match very well, but not quite exactly, with splits in another tree and assign some sort of score to those. But there hasn't been a sort of a principled way of assigning a score to that. So what I've proposed is to use information theoretic methods. So to say, well, how much information is there? And ultimately the goal is to say how much of the information in tree A is also present in tree B. From using an information theoretic definition, or it can be measured then in bits. So that's not quite what I've accomplished. It's relying on splits rather than trees, but it does allow us to compare tree distance in a way that's got a unit, and so is in some way a meaningful quantity. And it also outperforms all other tree distance metrics across a variety of properties that we might want it to do so, and it can be calculated reasonably quickly. So I suggest that this is a method that we should be thinking about using. It often gives different results actually to the Robinson folds, and might change the outputs of analysis.
Fantastic. Is there any questions for Martin? Anything online? I've got a question for you. I really like the way you explain information theory. It was a good reminder. I also like how you used it to calculate distance matrix, which I think has lots of uses. I wonder if you could do any, have you thought about doing other like matrix-based statistics on that matrix to further describe, say, differences in host parasite or whatever?
So which matrix are you referring to precisely? Do you mean the distances between splits?
Yeah, difference between splits, yeah.
Yeah, I guess I'm only really using that matrix to find an optimal matching between splits. So no, I've not taken that any further, but it'd be interesting to think of what else it could be used for, certainly.
Yeah, sure.
I had one question along those lines. Have you had any thoughts on how you might be able to use it to create a consensus tree?
Yeah, it's certainly it certainly seems like it could be useful in that way. And I think, to some extent, taking a strict consensus is very similar to taking a Robertson-Folds distance. Yeah, sort of the resolution of a strict consensus.
Sort of very fragile. Yeah.
But I think that there are challenges, and I guess one thing that I think, a direction that I like to go in is to take a sort of, to extend this to say, well, it might be possible to identify a taxon that is consistently in the splits that match very poorly. And so actually, if we take away that taxon, we can get a very well-resolved strict consensus of all the other leaves, and then we have this other taxon that's floating around. And you can imagine taking off a subtree that's plotting. So maybe in this Lis amphibia example that Anna was presenting, there's half of the clade that sort of could plot on this side of the tree, could plot on the other side of the tree. Maybe the relationships within that clade are well resolved, and you could plot that clade, and maybe the relationships in the rest of the tree are well resolved. And so having two trees in that way could maximize the information content of your consensus tree. So this idea, I guess, of a most informative consensus tree, which may comprise multiple segments, and we don't know quite how they fit together, I think is something that could be tractable by a continuation of this approach.
Well, thanks very much.
Any other questions for Martin? Okay, we can come back anyway if you've got any in the meantime. So we'll have our go through our last recorded talk speaker, which is Olga from University of Vienna. I also really enjoyed your talk as well. And the technology was fantastic.
Thank you.
So.
Yeah, I was forced. Aunt forced me to do that. I didn't want it at the beginning.
It was great.
Thank you.
That's high production though. Put us all to shame.
I felt like a superstar. Doing forecast, weather forecast.
Weather forecast, yes, that's what I was thinking of. Looked like a weather forecast. Pretty cool.
All right, so the talk. When you analyze in multi-gene alignments, and there's some sequences which are missing there, what might happen that your tree space will be partitioned into sets of equally scoring trees, which we say they're phylogenetic terraces. So what's special about those trees that they have the same set of subtrees associated to partitions. And what we now want to do is, so having this set of subtrees, we want to generate all trees which are consistent with them, which belong to the same terrace. So this problem was studied in supertree method, and we know that it's complex. So the decision problem for unrooted trees is NP complete, and the counting problem is sharp P complete. So we don't expect to find any polynomial time algorithm, but we wanted to have something which might be useful in practice. And we came up with a simple idea of using a stepwise taxon insertion. So you would start with some initial tree which does not violate your constrained subtrees, and then you start inserting on a taxa one by one by still keeping track that you must be consistent with the subtree. So you will only insert taxon on allowed branches, and you will skip the forbidden one, which would violate the constraints. And then inserting taxon one by one to every allowed branch of every tree which was generated in the previous step, you will generate all trees which are consistent with this initial set of subtrees. And we were very surprised to see that on biological data sets, we really can generate all trees from a terrace within a reasonable amount of time. And it's super cool because now you can infer maximum likelihood tree with partition model, and then you can check so how many other trees which have exactly the same score due to terraces, due to this missing data. And if the terrace is really huge, maybe you want to change something in your supermatrix, so to delete species, to add sequences, or to remove some genes, or if the terrace is not too big, you just summarize trees using some consensus method. And for us, it's also cool because now we can use this algorithm to study the terrace structures for much larger number of species than just 6 or 7, where you can analyze whole tree space. So that would be it.
Oh, thanks very much, Olga, for that. Is there any questions for her? Yes, Mike.
So, Mike here. I'm interested in the camera's pointing over there, so never mind. So you developed a method that you ran that after a while you sort of basically go, okay, that's an awful lot of trees in the terrace. Have you, and it's hard to know exactly how many there are, but have you thought about any approximation methods to have a rough guess based on, I don't know, are you hitting the same trees again and again if you construct them at random or something like that?
So we also came up with sampling, Markov chain Monte Carlo sampling for terraces, but it becomes problematic because terraces can be disconnected and this sampling relies on connectivity. So yeah, so we're actually very happy with this algorithm because now we can check how often this disconnectivity happens, because then we can use this Markov chain Monte Carlo sampling to actually try to get some approximation for the size of the terrace. But for practical purposes, in fact, we maybe are not interested in generating all millions of trees from the terrace, but at some point you'll say, wait a moment, like your maximum likelihood tree lies on very, very huge terrace, do something, because it's not reasonable to get any hypothesis, to base your hypothesis on that tree. Yeah.
Thank you.
Cool. Good stuff. Any other questions? Is there any online? Feel free to speak up if you have any questions online. Anything in the chat? Well, I'd just like to thank the 3 recorded talk speakers. They've been fantastic as well. It's a challenge to do, and I think they all put it off very, very well. So thank them again. And I think that's, oh, Jeremy's got something, no? I think that's it for tonight's session this morning. Just for those not in the room, Jeremy's putting its beer o'clock, which it is. So we're all off to the pub.